Welcome to Take Electricity Seriously, Developing Awareness. This videotape provides an overview of why electricity is so important to us and how we use its constructive power every day. The program also illustrates the destructive power of electricity in very personal ways. This program will heighten your awareness of electrical hazards, helping you to think about safety before doing anything that involves electricity. Let's watch.
From the lightning in the heavens to the iridescent images of the city's skyline, electricity pervades all facets of our lives. It is indeed a marvel, and a convenience few of whom would do without. Ben Franklin may have brought electricity from the heavens to the earth through kite strings, but it is Thomas Edison who is mostly responsible for harnessing electricity and bringing it into our homes. In fact, Edison is known more for his distribution system than for inventing the light bulb. Joseph Swan of Great Britain actually introduced his carbon filament light bulb an entire year before Edison introduced his. But it was Edison who conceived and implemented a distribution plan with a network of generators, meters, and wires that kept his bulbs burning for long durations of time. Electricity was introduced into the home, bringing about changes undreamt of before 1879. Electricity has turned our personal castles into modern wonders of the 21st century. Never has the homeowner had so many electrical devices to play with. Television, a marvel in the 50s, now seems to be a natural part of our culture. We have a whole generation of young adults who cannot remember growing up without the television set. But for all its magic, it can still remind us very quickly that people are still people and that people make very serious mistakes. What I'm about to show you is tragic and regrettable, but also a vivid image of what this campaign is all about. A television news crew in North Carolina went out to report from the scene of an automobile accident. Their preliminary information stated they would not be covering a tragedy, only property damage and some minor injuries. The accident involved this car, which hit a telephone pole and brought down the power lines. As you can see, the rescue team is treating the driver directly under those lines, which everyone assumed were not energized or live. This will prove to be an unfortunate mistake. As the cameraman turns to film the damage, we hear the shock as a worker stands up into the lines and is hit with 7,200 volts. This worker is fortunate in one respect. He had an entire rescue team right there to react and save his life. But notice the contracted body, the muscles locked in position, the body shaking involuntarily. This is the terrible result of contact with electricity. Those of you who work with and around electricity know the reality of this situation. This is why the company expends great resources to substantiate, institutionalize, and train people in the safe handling of electrical equipment. But for many of us, this is as close as we get to electrical devices, those that populate our kitchens, workshops, and family rooms, and we have plenty of them. Those that assist us and those that entertain us. One of the more enjoyable ones is this, the camcorder. This device can bring the most joyful moments of our lives back to our television screens to be relived and shared again. What was once in the domain of news and documentary producers now is readily available to the consumer. But much like the evening news, this device can also remind us of tragedy in our lives. What if while we were using our video cameras, we actually filmed some of the careless tragedies acted out every day around our homes. Suppose you were a homeowner having your house painted and you went out to shoot some videotape of the progress. You walk out further to the front yard to get a better overall look when one of your neighbors speaks to you. You are momentarily distracted as you make conversation and forget to turn off the camcorder. You are unaware of how close the painter is working with his aluminum extension roller to the power lines attached to your house, until it happens. A situation repeated often by homeowners who also install antennas on their roofs. With simple awareness, he could have avoided this tragedy by working with wooden or fiberglass tools, and more importantly, by working carefully near the power lines. Or suppose you are with a relative who is experiencing flooding problems in his basement. The storm is still present outside as he attempts to retrieve some belongings. He's asked you to shoot some video for his insurance purposes. While you assist with the camera, the water continues to rise until it's over his ankles. Unknown to either of you, the water is also making contact with the fan motor on the heater unit. Then it happens. He trips over something hidden in the water. He instinctively reaches out to grab hold of anything. At contact, the fan motor charged the water. As he reached out, he grabbed the water pipe, which is often used as a method of grounding in homes. Making contact, he completed a circuit for the house current through his body to the ground. What was so important that he had to go into the basement with a storm still in the area and the danger of power sources being flooded? Suppose your son attempted a prank, hoping to sneak up on his sister with the video camera while she made up her hair. He achieves his goal as she is startled and drops the hairdryer, but into the sink, half filled with water. The humor only lasts a moment until she absently reaches for the hairdryer. Stunned from the brief electric shock, she falls unconscious. Had her fall not broken the connection, she would have been killed. One has to wonder why an inexpensive GFCI was not installed to prevent this incident from happening, much less the proper teaching of children as to the dangers of electricity and water. Suppose you were shooting some memories of your son before he leaves for college. He happens to be washing his car with the vacuum nearby. He has already washed soap suds to the driveway surface. He is using an extension cord that has been worn open in one place. That little opening, coupled with his bare feet, combined to create a fatal combination. Although the vacuum is a grounded device, the exposed wire touching the water is similar to the basement tragedy. As soon as he touches the vacuum to turn it on, the connection between the wire, the water, his feet, and the grounded vacuum is now complete. This fall breaks the connection, but not before heart fibrillation has begun. Without immediate medical help, he will die in the driveway. Again, water and electricity are involved. However, simply checking a cord for frayed ends, brittleness, or an obvious exposed wire could have prevented this tragedy. Possibly even wearing leather or rubber-soled shoes could have saved him. You could be on vacation returning to your trailer home just after a storm has passed through. While assessing the damage, you take a few pictures for your personal record. You are looking at the damage and the branches that have fallen on the trailer. Your husband reaches up to drag a branch off the roof. As he does so, he is knocked to the ground by an unseen force. He is dazed, but will live to tell the tale. In his haste, he neglected to see if the branches were in contact with the power lines leading to the trailer. This is a situation much like the painter on the ladder. The limb, like the aluminum pole, creates a circuit to the ground through his body, which can cause similar injuries and/or death. His rushing into the situation only made it worse. And so it goes. Every day, every month, every year. It becomes very clear that we have welcomed electricity into our homes and put it into service for our every need. But But it is also obvious that we still do not harness it correctly in all situations. But we can, with knowledge, willingness, and the proper response. For instance, water and electricity are a dangerous mix. If you aren't trained in how to work in a wet area, why experiment? Do you use double insulated or grounded electrical tools? You know what they are? Do you look for the UL label on tools as well as cords before you buy or use them? Do you ever use an adapter to make a 3-wire plug fit into a 2-wire receptacle without using the safety feature? Do you use GFCI receptacles in bathrooms and kitchens? Do you think that making contact with an outlet or circuit will result in a small tingle, nothing worse? Do you really want to find out? Do you know how to verify that the power is off before working on a circuit or changing a switch? Have you taught your children the proper respect for electricity? For instance, we're frightened of lightning and we stay away from it. Now, that's not a bad starting place when it comes to electricity, especially if you have no reason to manipulate or alter it.
I was drilling through the wallboard when I evidently struck the 220 line. It coming into the house, when it shocked me.
So I was holding on to this thing. When the antenna hits a power line, blows a hole in its foot the size of a silver dollar.
Oh, listen to me now. It's gotta have been foregrounding or something in the electrical service. Because the outside shell of the trailer, the entire outside, was energized. And you couldn't touch it.
We had turned the light switch off while putting in the ceiling fan. But my son walked in and said we needed more light and turned on the switch.
I was wearing the watch during this simple job, and it grounded me out. And the shock was so powerful that, well, that's when I lost my hand.
It was the only outlet without a safety cap. And in the few minutes I left him alone, he found a way to put my car keys in the outlet.
I just simply removed the wrong fuse. When I cut across both wires, it melted the pliers. It scared me bad, too.
And the time it took me to turn off the breaker and walk back to the problem, someone had come along and turned the breaker back on. I could have been killed.
When Edison created his light bulb, he knew he had to create an entire system that would bring electricity to these bulbs wherever they were located. And he knew he had to do it safely. The planning and effort that went into our present system to provide us with the power and conveniences we enjoy involved hundreds of people. But the planning and effort that goes into keeping you safe comes from only one person, you.
Something we can't see makes our modern world possible. Electric power. Big power for industry. Small power for homes. Electricity is a friend. We're not too much afraid of it around the house. But lightning and high voltage seem dangerous. Look out. The current to light a 100-watt bulb could kill 20 people. The electric energy to toast a slice of bread could kill 200 people. An electric iron, 300 people. The current that must pass before a 20-amp circuit breaker trips could kill 10 busloads of people. Every year in North America, over 1,000 people are electrocuted by accident with tools, radios, appliances no one was afraid of. And according to U.S. Public Health Service estimates, 30,000 people are injured each year in accidents with wall sockets and extension cords alone. This is not to mention the hundreds of thousands of fires in homes, plants, and schools that are caused by line-to-ground faults in electrical systems. Have you ever felt a tingle when you switched on a lamp? Here's why you're still alive. Electricity wants to go to ground. It will take the best route available. It would rather have a wire, but a human body will do if there's no choice. So your body becomes part of the circuit. The lamp switch that tingles and is leaking current because of a defect hasn't hurt you, because you're insulated from the ground. Some substances are better insulation than others. Dry shoes and a thick carpet do a good job. In this case, they could save your life. But suppose you were grounded. The garbage disposer switch is defective and tingles. You have your hand on the water faucet and touch the switch. Through the pipe, you are connected to ground. Electricity wants to go to ground. You are now part of the circuit. It is current, measured in milliamperes, that shocks and kills. Here, volunteers demonstrate some effects of small but dangerous current. The subjects have all been given medical examinations and are ready for the test. The current in the conductor this man holds is measured in thousands of amperes, or milliamps. At between 9 and 16 milliamps, a man reaches his limit of ability to release the conductor. This is his let-go current. Not being able to let go, she freezes to the conductor. In an actual situation, this acts to trap the victim. She is getting about enough current to light a pencil flashlight bulb. She suffers painful muscular spasms. At this point, we will have to cut off the current. When current of the order of 50 to 100 milliamps flows through the victim's chest, ventricular fibrillation occurs. The heart is overstimulated. Its rhythmic pumping action is disrupted. Then, heart action ceases, and death follows soon after. Again, this is current in the neighborhood of only 50 1/1000ths of 1 amp. But how often does such a dangerous situation occur? In many electrical devices, there is leakage of current. Insulation becomes worn or broken. Tools develop a hot case. Appliances and radios, a hot frame. Contact these while partially insulated, and all you get is a tingle. But if you touch a grounded metal object or stand on a wet floor or grass in bare feet, the tingle becomes a lethal shock. Many appliances and tools come with the third prong for use in 3-hole grounded outlets. But older homes have no such outlets. So the third prong is often broken off. Or an adapter is purchased, and the wires intended to ground the tool or fixture to a metal outlet are ignored. Add to this, many outlets are improperly wired, and the third hole leads nowhere. Certainly not to safety from line-to-ground faults. And many so-called grounded systems have undetected breaks, worn wires, or other defects that are developed and cannot be depended upon for safety. This leaves the average person at home, on the farm, and in many types of industry exposed to danger from leaking electrical currents. Swimming pools with current-leaking light fixtures create electrical fields in the water and cause many deaths by paralysis of the human breathing mechanism. This is called anoxia. Hot deck fittings, boxes, and pump motors also contribute to electrocutions. Of course, the ordinary circuit breaker offers no protection to people from line to ground faults. In many cases, a life was at stake. What could be done to detect such faults instantly and cut off the power within milliseconds? The answer was found by Charles F. Dalziel, professor of engineering at the University of California. He discovered and patented a device that is known as the GFI, or Ground Fault Circuit Interrupter. It can eliminate ground fault dangers. This is a ground fault detecting mechanism. It consists of a differential current transformer with a special magnetic core and a solid-state network which activates a current interrupter. The transformer totalizes the current flowing through identical primary windings. As long as the current is normal, the output from the transformer to the solid-state network is 0. But if for some reason current, that is, leakage current, is diverted to ground on the load side of the transformer, a resultant flux will be produced in the core, inducing a voltage in the secondary winding. This voltage in the secondary winding actuates the solid-state network, which results in tripping the current interrupter. So to all intents and purposes, the instant the conductor and ground are touched, the power is cut off and the subject receives a harmless shock. Ground fault protection is now available in a new form, the GFI duplex receptacle. Compatible with any fuse or circuit breaker overcurrent equipment, this device easily replaces any standard outlet. It can be installed to protect its own 2 outlets only, indoors and outdoors, with a rainproof cover. Or when installed as the first outlet from the fuse box or breaker panel, the GFI receptacle will provide ground fault protection to all of the outlets on that circuit. So now, there is no reason whatsoever why anyone, anywhere, need fear line-to-ground shocks. Because the GFI, which detects death-dealing currents and responds by cutting them off within milliseconds, is now available to everyone who needs protection. This is anyone who uses electric power, the fantastic force that makes possible most of the wonders of our modern world.
Can your facility handle the electrical needs of today? Is it ready for the next decade? Smart building owners and developers know that having a facility free from power quality problems is a bottom line issue. Electric codes are primarily safety related and do not adequately address power quality concerns, such as erratic operation of computer-based equipment, overheated equipment and wiring due to harmonics, voltage sags and surges, premature equipment failure, nuisance circuit breaker tripping, and others. Preventive measures and design considerations which can lessen occurrences and effects of power quality problems are relatively inexpensive to install during a building's construction or renovation. They are also cost-effective. This program will help you to better understand one of the most important power quality concerns, harmonics.
A mystery is occurring in today's office buildings and manufacturing plants. Transformers and neutral and phase conductors are overheating. Circuit breakers are tripping, and motors are burning out for no apparent reason. Yet the standard troubleshooting tools and procedures show everything to be normal. So what's the problem? Finding the problem is relatively easy once you have the right tools and know what to look for and where. This program will help give you a basic understanding of power system current harmonics. It includes some pointers on how to identify harmonics, as well as some methods to address the problem. Harmonics are frequencies that are integer or whole number multiples of a fundamental frequency. If you strum an instrument in the middle, the strings vibrate at the fundamental or lowest frequency. If you strum near the bridge, the strings vibrate at the fundamental as well as at one or more harmonic frequencies simultaneously. In this way, the fundamental combines with harmonic sine waves to form non-sinusoidal or distorted repetitive wave shapes. In power systems, harmonic currents or voltages are multiples of a fundamental frequency. They're present in the distorted waveforms created by nonlinear loads. To understand, let's first look at linear loads. Under normal conditions, the voltage waveform supplied by an electrical utility will be a sine wave at the fundamental frequency. When a linear load is connected to a sine wave voltage, the current will always be a sine wave at the same frequency. In other words, a linear load does not produce distorted current when connected to a sine wave voltage. When the load contains nonlinear elements, the circuit may draw current in abrupt pulses rather than in a smooth manner. These pulses form a distorted current wave shape which contains harmonics. Harmonics are prevalent wherever there are large numbers of nonlinear loads, such as personal computers, lights with electronic ballasts, electronic office machines, and adjustable speed motor drives. Equipment that typically contains a switching power supply that has a nonlinear diode capacitor input circuit. This type of circuit converts AC voltage to DC to charge a large capacitor to the peak of the line voltage. The equipment then draws DC current from this capacitor to power the rest of the circuit. As the voltage goes through a complete cycle, the circuit draws short pulses of current only during the peak of the line voltage. This causes the current to become distorted, and it's this distortion which contains harmonics. This load can be represented by a resistor in parallel with several current generators operating at harmonic frequencies. The resistor conducts current at the fundamental frequency. The harmonic current generators pump out current at higher frequencies. These all add together to form the distorted current drawn by the nonlinear load, which enters the power distribution system where the load is connected to the power line. Each harmonic has a name, frequency, and sequence. In AC power distribution systems, the positive and negative portion of the current and voltage waveforms are nearly equal, so no DC component is present. Under these conditions, the even-numbered harmonics will not be generated. The remaining harmonics occur in 3 sequences in terms of the effect of their phasor rotation. The higher the frequency, the faster the magnetic field rotates. The positive sequence harmonics, including the fundamental frequency, are forward rotating. In other words, when applied to a 3-phase induction motor, the rotor will rotate in the forward direction. The magnetic field produced by a negative sequence harmonic tends to cancel the field produced by the fundamental and rotates in the reverse direction. This effect can cause 3-phase induction motors to burn out. And zero-sequence harmonics, known as triplins, don't rotate. Instead, they add in the neutral of a 3-phase 4-wire system. Most of the harmonic current found in the neutral is due to the 3rd harmonic. The effects of harmonics show up in the power distribution equipment that serves both the single-phase and 3-phase nonlinear loads. Single-phase nonlinear loads are typically 120-volt receptacle and lighting loads found in offices and commercial buildings, while 3-phase nonlinear loads are usually found in industrial plants where there are large motors with adjustable speed drives. Harmonics from single-phase nonlinear loads enter the system through receptacles and then cause heating in phase and neutral conductors and bus bars. At the load center, harmonics can cause premature circuit breaker tripping due to heat and frequencies greater than the 60 Hertz rating. Shared neutral conductors in a 3-phase system can be severely affected by nonlinear loads connected to the 120-volt branch circuits. Under normal conditions, for a balanced linear load, the fundamental 60 Hertz portion of the phase current will cancel in a shared neutral conductor. However, triplen harmonic currents add together rather than cancel in a shared neutral, which results in neutral current that can be greater than the phase current, even if the loads on the phase conductors are balanced. This neutral current can typically be 130% of the total current measured in any individual phase. This situation is worse if neutrals are downsized. Again, the danger is overheating because there's no circuit breaker to limit the current in the neutral conductor. Excessive current in the neutral conductor can also cause higher than normal voltage drops between neutral and ground at outlets. Neutral bus bars and connecting lugs are sized to carry the full value of the rated phase current, but they can become overloaded when triplen harmonics add in the neutral conductors. Commercial buildings commonly have a 208 120-volt transformer in a delta Y configuration, which feeds receptacles in the building. When triplen harmonic currents in the neutral reach the transformer secondary, they're reflected into the delta primary winding, where they circulate and cause overheating and transformer failures. The same type of problems occur in single-phase systems with lighting loads at 277 volts. Once you have the right tools, a location survey will help you find out whether or not you have a harmonics problem and where it's located. Walk through the building. Look for personal computers and printers, adjustable speed motors, solid-state heater controls and dimmers, and fluorescent lighting fixtures equipped with electronic ballasts. If this type of equipment is present, chances are the electrical system contains harmonics. The next step is to locate the transformers feeding those nonlinear loads and check for excessive heating. Also, make sure the transformer cooling vents are unobstructed. Using a true RMS meter, measure the current in each phase and in the neutral of the transformer secondary. If it's a 4-wire system, compare the current measured in the neutral to the current estimated from the imbalance in the phase conductors. The neutral current would normally be 0 if the phase currents are equal in both amplitude and phase. If the neutral current is unexpectedly high, triplen harmonics are probably present. Next, measure the frequency of the neutral. If you're getting a reading of 180 hertz, the neutral current consists mostly of third harmonic. Compare the phase current readings to the rated current calculated from the nameplate kVA. For a linear load, the measured reading should not be higher than this value calculated from the nameplate. Survey the sub-panels that feed harmonic loads. Measure the current in each branch neutral and compare the measured value to the rated capacity for the wire size used. Check the neutral bus bar and feeder connections for heating or discoloration. Also measure the frequency of all the neutrals. Again, 180 hertz indicates the presence of third harmonic. There are a number of steps that can be taken to minimize harmonic problems in the design of new facilities. First, using a true RMS meter, determine what the actual load currents will be for specific types of equipment. Then, wherever possible, design for this known load current. Reduce the number of receptacles per circuit to allow for the extra voltage drops caused by harmonics. Pull extra neutrals in branch circuits or use oversized neutrals. Use oversized feeder conductors and conduit for better heat dissipation. And also oversized load centers so that bus bars will not be overloaded. Or use load centers rated for nonlinear loads. Specify harmonic-rated circuit breakers in the design. Require a harmonic-rated transformer with a K-factor appropriate for the load. Arrange branch circuits and feeders so that three-phase induction motors are not connected to circuits serving nonlinear loads. Wherever necessary, use isolation transformers. And specify that the people doing maintenance on the system be equipped with true RMS measuring instruments.
An important part of analyzing the power quality for a facility is to do a harmonic survey. We'll do an abbreviated version of a survey looking at 5 key areas. In each case, we'll use true RMS tools to make some key measurements which can help you identify potential problem areas. The results can also help if you need to communicate with a consultant. The load capacity ratings for most electrical components are expressed in terms of RMS voltage or current. Since the RMS value is defined in terms of heating effect, it's essential to use true RMS tools to make measurements on power distribution systems. Commercial buildings often use a delta-Y transformer to feed single-phase receptacles. Nonlinear loads connected to these receptacles may produce triplen harmonic currents, which add algebraically in a shared neutral. When these currents reach the transformer, they're reflected into the delta primary winding, where they circulate and may cause overheating and transformer failure. When harmonics are present, a true RMS current reading is essential for accurate comparison to nameplate ratings. To find harmonics affecting a transformer, measure the current in each phase and the neutral of the transformer secondary. A harmonic spectrum display shows the relative amount of individual harmonics in the phase current. In this case, the third harmonic is 41% of the fundamental. On the transformer secondary, determine the harmonic rating, or K-factor, of the phase current. The K-factor is a relative number that indicates the amount of extra heating that can be generated in a standard transformer by a particular combination of harmonics. This number can be used to select a replacement transformer designed to supply nonlinear loads. A K-factor of 1 indicates no harmonics. Phase currents in a commercial office building supplying computer loads can have a K-factor of up to 9, but a typical value for a commercial building is 4. Individual branch circuit currents supplying computer loads can have K-factors of 15, but the K-factor at the transformer secondary will be much lower due to harmonic cancellation. If there are significant levels of current harmonics, there are some steps that can be taken to reduce the chance of transformer failure. Solutions, however, vary depending on system wiring configuration. A solution which works in one type of system may actually aggravate problems in another. One option for a conventional transformer is to derate it, or operate it at a reduced load rating, using an industry-accepted derating formula like the CBMA one. Then label the transformer with the lower load rating. Harmonic filters can be applied to load centers to reduce harmonic currents in the transformer and also solve other system problems. Filters must be carefully designed to meet the needs of individual systems based on detailed harmonic surveys and system impedance calculations. An existing transformer can be replaced with a harmonic or K-rated unit. The K-factor of the replacement unit should be selected to match as closely as possible the measured K-factor of the phase current at full load. A replacement transformer with too high a K-factor may actually increase harmonic currents due to its lower impedance at harmonic frequencies. Wiring configuration, existing load conditions, and anticipated changes in loading should all be considered when design changes are proposed. At the load center, harmonic currents can cause circuit breakers to trip. Thermal magnetic breakers may trip prematurely from excess heat in the panel caused by harmonic currents. These breakers may also trip erratically if nonlinear currents with high peak values are present. A peak sensing circuit breaker responds to the peak of the current waveform. Since the peak may be higher due to harmonics, this type of breaker may also trip prematurely at a lower RMS current. To detect harmonics at a load center, check the phase voltage for flat topping. Then, measure the currents in the feeder conductors using a true RMS instrument. Remember that these instruments indicate the actual heating value of the current, including harmonics. Verify that you're operating within the load ratings for the panel. Measure the feeder neutral current. If it reads high, tripling harmonics may be present. Then compare the measured current against the ratings for the conductors, lugs, and bus bars. Compare the individual branch circuit currents to the breaker ratings. Also check the branch neutrals for overloads from tripling harmonics. The same process can be repeated at the rest of the load centers fed from the same source. Once you are sure a receptacle panel is affected by harmonics, there are a few options to correct the situation. First is balancing the load. If the neutral current is 50 or 60 hertz, rearranging the branch circuits can reduce the neutral current. In some cases, the load can be redistributed to other existing or new panels. Zero-sequence harmonic filters can be connected to the panel to reduce neutral current in the feeders. Filters should only be installed after consulting with a qualified engineer. If the neutral conductor is overloaded, a larger conductor may be required. Or the existing receptacle panel can be replaced with a panel and main breaker rated for nonlinear loads. Excess heat caused by harmonics in lighting circuit conduit can cause conductor insulation to fail. In energy-saving electronic ballasts with solid-state power supplies, the phase and neutral currents can contain harmonics. Existing standards for the number of conductors in a conduit don't always account for the heat caused by these harmonics. To find harmonic overloads in lighting circuits, you can make the same measurements that are made at the receptacle load center. Measure the current in the feeder neutral. If the levels are high, compare the measured current to the ratings for the conductors, lugs, and bus bars. Feel the conduit for excess heat. To determine the overall level of harmonics, measure the total harmonic distortion in the phase currents. The THD generally refers to the RMS value of all the harmonic currents divided by the fundamental. The total harmonic distortion may be a problem if it exceeds 20%. To prevent harmonics from affecting a lighting load center, for new designs, you can specify fewer conductors per conduit. Or you can install new high-performance ballasts, which produce lower harmonic currents and also improve power factor. Induction motors can suffer from harmonic current heating if the supply voltage is distorted. And the presence of negative sequence harmonic currents reduces motor torque. The combination of these effects can cause motors to burn out. To find harmonics affecting induction motors, first measure the RMS voltage at the motor terminals and compare it to the nameplate rating. Then, look for imbalance in the phase-to-phase voltages. Look for obvious distortion in the voltage waveform. Then measure the total harmonic distortion. Most motor manufacturers recommend less than 5% voltage distortion for a fully loaded motor. Check the voltage harmonic spectrum. If large third harmonic component is present, the source is lighting ballasts or receptacle loads. If large fifth harmonic is present, it could indicate adjustable speed drives and other three-phase nonlinear devices are contributing harmonics. To minimize the effects of harmonics on induction motors, you can reduce the voltage distortion on the terminals by connecting the motor to a load center supplying only linear loads. Or you can consult with an expert and add a harmonic filter at the source of harmonics. Capacitors used to correct low power factor caused by induction motors can fail if harmonics are present. K-VAR correction capacitors can form resonance circuits at frequencies above the fundamental when combined with the inductive reactance of the distribution network. This is normally not a problem if harmonics aren't present. However, a harmonic current produced by nonlinear loads may find a resonance involving the K-VAR capacitors, and the resulting high current may cause the capacitor to fail. Examine the capacitor current for harmonics, typically 5th and 7th. Adjustable speed drives are a common source of 5th harmonic, so check the supply phase current at the suspected motor drive. The need for correction capacitors may be reduced when adjustable speed drives are installed on existing motors. Line reactors can be applied at the drive inputs to reduce harmonic currents. Or to avoid harmonic frequencies from resonating with correction capacitors, compensating networks can be designed to detune the resonant system.
Today's office, institutional, commercial, and manufacturing environments require that consideration be given to these recommendations for addressing harmonics and other power quality issues. Specify wire size beyond code minimums, especially neutral conductors. Reduce the number of outlets per circuit. Segregate sensitive loads on separate circuits. Always use a separate grounding conductor irrespective of the conduit. Use an isolated grounding conductor for sensitive equipment. Use a buried copper ground ring with multiple ground rods as part of the grounding electrode system. Provide lightning and surge protection. Use harmonic rated transformers, circuit breakers, and panels. Oversize phase conductors to minimize voltage drop and save energy. Select conductors and other materials based on their superior connectability and others. The Copper Development Association gratefully acknowledges the Fluke Corporation for supplying and permitting use of its programs, Understanding Harmonics and Managing Harmonics. For more information on harmonics, other aspects of power quality and energy efficiency issues, or for additional copies of this program, please contact the Copper Development Association and visit our website at www.copper.org.
Electricity, properly harnessed and controlled, is one of the single most beneficial discoveries known to man. It's become almost as much a part of our everyday lives as breathing. We live with it and enjoy its many advantages day in and day out. And certainly being on the job in today's world means dealing with electricity. It's a sure bet that you work with some form of electricity every day.
So what's the big deal? Well, each year, thousands of people die or suffer injury in the United States alone from electrical shock. You see, aside from being a great benefit to mankind, electricity mishandled or used carelessly is also one of nature's deadliest forces. Too many electricity-related deaths and accidents occur each year in the workplace. But you already take every imaginable precaution and can see any dangerous electrical situation, right? Well, if that's the case, why is it so many workers are injured or die every year because of needless electrical accidents?
Think for a minute to the day-to-day situations you experience in your job. When was the last time you were in too much of a hurry to wear your hard hat or insulated gloves? Can you recall a time when it was just too inconvenient to shut the main power off? Or maybe you observed a coworker who decided to skip safety because he thought he knew what he was doing.
Whatever the case may be, the big problem with electricity is that most of the time you don't get a second chance. One mistake, either carelessness or inexperience, can have deadly results. Let's look at the cases of 4 people who might have been your friends or coworkers. People just like you, who have family and friends waiting for them at home. We'll look at each accident. Then we'll explain why each incident occurred and how it could have been avoided. This first case involves 6 workers on 2 different shifts. And it illustrates the fact that when working with electricity, cutting corners on even standard safety procedures not only puts your own life in jeopardy, but the lives of others.
Two experienced electricians, Paul and Mark, traced an electrical problem in a high-powered piece of equipment. The problem was in a 440-volt 3-phase circuit breaker. They disconnected the breaker from the load side. Then they tested it electrically using a megometer and found it to be electrically defective.
Well, defective. Let me see it. Order another one.
After Paul removed the breaker, he placed it on a counter away from the breaker box. Mark proceeded by ordering a replacement breaker. They assumed that they would later install the new breaker when it was delivered. Therefore, both men neglected to tag the defective breaker as out of order. In addition, neither man communicated the status or location of the defective circuit breaker to their shift supervisor, and the supervisor failed to check back to see that the circuit breaker had been installed. Mark had every intention of installing the replacement breaker before leaving that day. Unfortunately, the replacement was not delivered until so late in his shift that he had no time to finish the job.
I'm out of here.
The second shift supervisor has assigned the installation to a second team of electricians. The problem is, no one on this shift knows which is the replacement circuit breaker. Not following company tagging and communication procedures has, in effect, created a potential disaster.
Here's a replacement breaker. I can't believe they didn't finish up. We'll never get this rewiring job done if they keep pulling us off of it.
Frank, it's only a circuit breaker installation. It's a 3-minute job. Let's get on with it.
Yeah, well, a bunch of 3-minute jobs add up to be a lot when you can't get your own work done. This just won't fit.
Well, Frank, the right one's got to be around here somewhere. They said it was delivered.
Hey, here it is, Frank. Here's the replacement breaker they brought.
Okay, I'll get rid of this one.
Well, everything looks all right with this one, Frank. It works mechanically, but why don't we get the measure and check it?
Look, we've been fooling with this long enough. That one didn't fit, so this has to be the right one.
Well, you're probably right, Frank.
How are you guys doing? You guys have been out here for a while. What's the problem?
Nothing major. See? Fits like a glove. I'm gonna close it now.
Well? Defective.
Impatience and not following proper testing procedures turned that potential disaster into a tragic reality. That man received severe burns and then died during surgery a few days after the accident. Even with the errors made by that first team of electricians, that fatal explosion could have been avoided. Let's review.
The first team neglected to tag the defective circuit breaker after removing it. Because they assumed that they would later install the replacement breaker, they neglected also to communicate crucial information about the breaker to their shift supervisor. But he, in turn, failed to follow up on the status of the job itself. The new breaker was delivered too late in their shift, so they did not finish the job. On the second shift, the supervisor was not aware of the status or placement of the two breakers when he assigned the installation to the second team of electricians. He should have waited to assign the job until he found out exactly which circuit breaker should have been installed. The worker's first mistake was not finding out the status of the job before proceeding. Even more dangerous was not de-energizing the system before beginning the installation. Secondly, they neglected to pre-test the replacement breaker's mechanical and electrical integrity. Had they done so, they would have known beyond a doubt that they had the correct circuit breaker. Now, when the electrician brought the defective circuit breaker over, he tested it only for mechanical integrity. Although it was available, he did not test it with the megometer for its electrical integrity. In their impatience, they assumed that because the second breaker was okay mechanically, it must have been the right one.
Those assumptions, along with their impatience to get the job done, cost one man his life. No matter how hard you try to justify them, shortcuts and impatience have no place in the electrical work environment.
These workers took a shortcut in the most basic electrical safety practice, not de-energizing. De-energizing is your best method of protection in an electrical environment. However, remember that even though equipment has been de-energized, An electrical shock can still occur because some equipment is fed by more than one power source. And remember, some circuits can store a deadly electrical charge, which